Yeah, okay. Now it's being recorded. Uh, so I all of a sudden feel nervous. Okay. Yeah. So what do we want to do today? So I could just go ahead and just go through a lot of live coding in Excel. I want to show you how we can build deep learning architecture from transformer to a lot of new stuff. Or do you also want to take stop to take questions? How interactive is this session supposed to
It
be?
gets it gets pretty interactive. People talk in chat. If there's anything interesting, one of us
Okay.
will let you know, or people might unmute. But pretty free
Yeah.
flowing. I think we
All
do it
right.
the same way. Like we don't really look that deep into benchmarks. We kind of skip that. People can look at numbers themselves, but
Okay.
fairly interactive.
Sounds good. We'll try to be interactive as if I'm teaching. This is more like a club. It's more a club rather than lecture. So I want to be more interactive. I'll stop and I'll take questions and I also ask questions to you too. So you have a lot of things you know better than I do. So what I want to share is my live Excel spreadsheet. So I've been using this a lot to teach deep learning architecture. And so this is sort of my plan to take you from Vision Transformer to Llama 1, 2, 3, 4. And there's a few these things are being introduced you might have heard of or read about often at the paper. So we'd like to talk about rope, talk about IMS, norm, talk about group query attention at Llama 2, and flash attention, interleaf attention from Llama 4, mixture of expert, a bit more like high level. Well, I wouldn't say high level anymore. It's a Excel level overview of what is happening, some live coding. And so I would like you to go to, I actually prepared a link for you to download to help access to the spreadsheet very easily. Let me just find the link. I should be a bit more prepared, but I don't know why. So how can you give me if some of you might have access to the document already, and maybe you can see a thumbs up so I know how many of you.
I just
How
shared it in the Zoom chat, by the way.
I mean,
If
I'm going to
people,
share on the Zoom chat right now, and so you have direct access. Wait, where's my Zoom chat? Okay, this here is
We
my
also
Zoom.
put it
Okay,
in the
I should have another version. So that is like they have to have the mailing list subscription gate. So this is a non-gated version of the link. You can go there and you will see you will see the top link is a live version of the same Excel sheet, and there's also a baseline version that I'm not gonna touch today, so you can compare how things evolving. And so that's what my plan to do. And quick overview of my transformer, vision transformer architecture that is expressed in Excel. If you will zoom out, you can see this whole stack from the input stack, normalization, self-attention stack to feed forward and output layer, softmax linear layer, and loss gradient. And we're going to do that and want to explain this. And the reason I picked this is that the transformer stack part is pretty common across modalities. So I picked Vision Transformer so that just to get an idea. Anything that it could convert your input into some tokens, you can put it into transformer stack out from this point. This is where transformer encoder started, or decoder. In this case, it's the encoder, but for GPT, it's a decoder. Anyway, so let's take the first challenge that so I hope that you could probably just get it right away because technically you have seen transformer before. You might not have seen this format, but you'll get it very quickly. So what I want to bring your attention to the attention layer here that I would like to show you how I would start by. Let's go back to my plan. My plan is to just to get well from transformer to llama 1 to 3 4. A lot of things scale up, just increase in dimensionalities. So we're gonna see how it is like. We're gonna focus on query and key. If we increase query and key, what happened? So if I increase query and key, so in this case, I want to read this a little bit. So we have input. This is a if you go out a little bit, these are tokens. We have 10 tokens here. And so here, 1, 2, 3, 4 are the embedding dimensions. They're currently 5. And so this will be input. And to start from attention stack, we'll multiply with all these weight matrices. I get so this QWK. So this one will then So we have query and key here, and then we get attention with dot product scale attention, and with softmax, that's how you can read it, and you can see it per column. This is softmax give a distribution, and then you multiply with your value. That's how attention sort of work, the way I visualize it. And so what happened is that if I want to add, so this is 3. The key dimension here, you can visualize 3, and over uh, 1, 2, 3, 4, 5 for 5 tokens. Okay, so far so good. And then what happens if I want to add 1 dimension? What I would do live is I would just shift this up down here. So I have this is kind of broken now. So I can add some more weights like this. Okay, and now it become a problem here is that if I like to get my keys over here, maybe use my keyboard instead. I hope you are following me fast enough. Okay, so here I have my query over here because should have 4 dimensions. Let me remove this, push it down a little bit more. So I have 4 dimensions for my query. So I have 4 dimensions. Now this scaled up dimension, scale product is broken because my key still have 4 dimensions. So I do something similar for my key as well. So I'm going to move down and then introduce a few more, initialize some random weights. Maybe it's 0 here, and then I'll update my equation here. So now I just managed to add 1 dimension. So now if you see this inductively, you can see how the things scale. And the takeaway is that the key and query, they should have the same dimensions, 4 and 4. But value doesn't have to be, but even though typically we keep the value the same dimension for convenience reason, but theoretically, this is the way you can visualize that the key and value increase in size. And what happened if we want to add 1 more token? So let me see, I check this. So I check this, maybe use this highlighter to say I'm done with this. Okay, and when I add key and value dimensions, you realize nothing else changed other than the computational complexity per cell. Now you have 4 things to dot product with. Okay, here, matrix multiplication, softmax. This is the raw implementation of softmax, and we have another matrix multiplication here. Okay, all right. So, and what happens when we want to add value? Says you want to add to 5, just to prove my point that they don't need to match my key and query dimension. Okay, and I have 5 of this. Okay, and then so then I have 5 over here. Now ugly, let me just add some more space here and insert here. And now I have this 5 over here. Now all of a sudden my attention weighted values from this attention head is 5 dimension. And now I'm going to zoom out a little bit to see what's going to happen if we can count attention head. Now we have first attention, second attention, third attention head, and we have things that collect them. So this is where concatenation happens. Now we have 2 extra dimensions for my values, and now it's no longer fit. What I can do is that I'm going to increase my dimensionality of the attention weighted picture from the first head and move up here. Now you can see that it will all fit. Okay, so I have 5 from first head, 3 from second head, and 3 from third head. This is 3 head multi-head attention. And then, but this is kind of important because my embedding dimension is 5. And then it had to be 5 consistently throughout your stack so they can put it all together. But now I have 1, 2, 3, 5, 1, 2, 3, 5, 6, 7, 8, 9, 10, 11, 12, 12 to 5. That's what we need to project. So I have to introduce more weights. So I want to introduce three more weights. So I just copy over here. And then I update my multiplication linear projection. All of a sudden, things are working again. Actually, I had too many. I actually had 2 instead of 3. Okay. Okay, so I'll kind of check my task. Okay, all right, now match is working again. So I just added 2 dimension to value for the particular attention head, and I show you how everything else change. Okay, anything else? How focus cell makes green across along the spreadsheet here. View, show focus cell here. and select your green color. I found green is pretty good for my class and to help you focus on attention. Anything, any question? Okay. All right. Where was I? Okay, so I checked the value size. I just changed it. Go back. And vocabulary size. Let's just talk about vocabulary size. So at the end, we want this model to output a word and a probability distribution across the word. So at the end, we still have, remember this is final output from encoder, still 10 tokens, each token has 5 dimension. Is it but supposed to be a vocabulary of 20 words. In this case, for original vision transformer, there's 20 class problems that we take the first head token, this is a class token. So we need to project from 5 to 20. So now you can visualize this linear projection right here. So this is what linear in the last thing, taken to the last thing of your transformer stack. And you do a softmax. Let me just zoom in a little bit. So you could see these. These are the values. Though this are the value could be arbitrary number, uh, but we want it to become a number between 0 and 1 for probability. But also, all these numbers have to add up to 1 for probability distribution. That's why we need softmax. So this is linear and softmax. Suppose we want to apply. So as you can see, for Llama 1, 2, 3, 4, it goes from where is the vocabulary size? From 32K, 32K, 128K. So it's going to be multilingual models, even more 250K because it's multilingual, multimodal mod. They want to have more things they can predict. Okay, so, and then that progression is mostly reflected in the last layer. So instead of 5 to 20, for instance, we want to go from 20 to 30. What do I have to do? So where do we have to grow this? So maybe a little bit too much. Let's just grow 5 by 5. So what I would do is that I would just 1, 2, 3, 4, 5. Select 5 rows and insert. And then I have to fill in this row. That's just initialized to 0. Maybe I just copy all my 0 over here. And these are all the biases. Minus to 0, 0, 0, 0. And now randomize it a little bit, but adding some random 1 here. So now I updated the score here. And then so I also have to do that updated by softmax layer, added another 5 row in the middle. So I have now these equations get updated. So I just increased the vocabulary size from 20 to 25. So that is where you will increase. But interestingly, as you can tell, the only thing I touched is the very last layer. I didn't have to touch any internal of yours of the transformer stack. Okay. So if you want looking for this sheet, so I have I could use this one. This is the link without, there's no newsletter subscription requirement. Just go there and just grab stuff that you can follow this. And all right, so let's go back to the number of vocabulary size. I looked at it now. And embedding dimension is a bit difficult to change. I'm not gonna change. I just say if I have to change, I have to change here. This is a token. So this will be this is the from image patch to token, about 9 to 5. So 9 is because of a 3 by 3 window here and got flattened into a column vector of 9. But for the language application, you can think of it as from a word in the vocabulary to in the embedding. And so we have 5, embedding space of 5. If I want to add one more, I will have to add one more row here. But the problem is everything else have to be extended by 5. This all had to change to 5. There's a lot of things I have to change. So I'm not gonna do that. So well, I just restore it. But what I want to do, actually, maybe I do want to do it for let me just do it. But I'm not gonna change the whole thing. So now I just add one dimension. Where else do I have to change? So this will go to the norm. So this has to change to 5 as well. And this is the most important. If I have a 5 of this, I have to move this weight, I have to add another columns of weight in order to multiply them well. So you can see the impact of adding more dimensions for your embedding is that you want your weight have to grow in this direction, like here. This is too much change. I don't want to change this. I'm gonna do that. So this I'm going to talk about it. So I maybe put a gray just to say that I sort of talk about it, but I'm not really implementing the embedding dimension change in my example. Okay, and then let's talk about group query attention, some attention stuff. So let's zoom out a little bit. I want to talk about now you see 3 attention head. What does it take to add another attention head? What I would do is that I would just create a more space here. Okay, and I could actually no, let's do this. I want to create more empty space. Ah, ugly. Let's do this. So I want to select here. Come on, let me do this. Select this. And this will be empty space for me to add some stuff. Whatever. Let's just, okay. So do I have enough space? Let's just do a little bit more space. So to get a new head into this, so what I can do is I will just copy this and copy this. All right. And now I have this weight as another set of weights. So in representation, I usually like to use red to highlight trainable weights. So these are all trainable parameters. When you hear 7 billion model, you are referring to this shaded red learnable parameters. So the things I do not shade means they are not trainable parameters. They do not count to the parameter count, but they still matter in terms of calculation. So they all need to be calculated. They all take up runtime memory. You have to all have to figure out how to fit into your GPU to optimize. But you can visualize computational complexity versus parameter size of the model. But when we talk about size of model, we tend to refer to these parameters. So here, okay, let's try to fix this. Where does it come from? So this come from, I had to fix this, but I could implement this. I'm going to zoom in a little bit. So what do? I want to take this, I want to implement matrix multiplication to take all theta weights, and then I'll go up and up to select. They all share the same input across this head. They all multiplying with this is the output from the previous layer, which is a norm. Okay, so this is how I implement it. So you can see this, and you can use F2 to examine this. So just to show you, I can scroll up to see, okay, this is where it's selected. And when I select this, okay, this is where it's selected. Select different kind of weight. Because I copy and paste it, so all the weights are the same right now, but I want you to purposely change a few things so they have 2 different set of weights. Okay, so now what I just manually implemented a new head, and the rest of it the same. So we have query. This you take the first 1/3 and to move over to the query, and take a second 1/3 and then put it on the key, but you have to transpose it. Maybe I can use my pen to draw it like this to show you the data flow, like here and here, and then you do a KT multiplication to get this dot product scale attention and scale it out with softmax. Softmax. Okay, how to write with my mouse. Okay, so I have a 3 different head. And what do I get? I get a more attention values here. We have to add this. We have to bring this 3 back here again. So let me just move up, move 3 spaces up. So create some space for here. I'm going to select here to concatenate. So what I'm implementing is concatenation. When you concatenate tensors, that's what's happening here. So if I do that and this whole thing get taller, so I have to extend my weight matrix sideways by the same length. So I'm going to copy 3 sets away here. And once I do that, I'll be able to update my matrix multiplication that it is linear projection over here to match. So if you read the paper, so usually they have says W out or down, what is it, down project. W down is referred to this matrix. This matrix can be pretty big too. But sometimes if you kind of divide your attention dimension in a way, you might not even need this. So suppose I, instead of having this many heads, suppose instead of 5, I have uh, say 100, and then we have 20 heads, and then each head have 5 dimension. And when that concatenate all of that, I get 100 back. In this case, you can skip this dimensionality change with this matrix. Anyway, so this is how things are impacting when I add one more head. So I do that. So add more head. Do I add more heads here? Where is it? Heads. Okay. When we add more head, that's what happened. So there's a head, adding head from Llama 2, Llama 3 over here. So I think I implement this. I'm going to put highlight this. Okay. Come back. All right, so any more? Let me see. I'm just monitoring the chat, but I guess maybe should I take one question before I move on? I want to talk about group query attention next.
Yeah, there's a question in the chat about vocabulary. How much does it cost in vocab size to add native understanding / generation of images and audio? So text-only Llama had 128K vocab, but multimodal Llama had 256K. I wonder if you want to address that
Okay,
before. Yeah.
so if I zoom out a little bit, the vocabulary size have only impact like in the output here. So you will grow this for output vocabulary. And if you have 3 modalities, this is get longer. And then you also need to figure out a way to convert your input into the embedding here. So this will be got a lot longer over here. But internally, once you pick the model size, this is gonna be the same. Okay, does it make sense? So
Yeah, that makes sense. We
yeah,
increase the number of
increase the
vocab.
number of vocab.
Mhm.
You increase the final projection over here in order to bring back also the initial projection. So let's just show you in the transformer in the so I picked this visual transformer for you to appreciate that input vocabulary and output vocabulary can be different. So input vocabulary, these are patches, and then they will project here 9 so you could into 5 dimension, but my output is 20 classes. So from 5 back to 20. Okay, so 2 things are independent, but they usually could be the same too, if one from language to language. Hope that works. Okay, let's look at group query attention. So what can we do to group them? So what happened is that, so just consider these 2 heads I just created. They look kind of identical. So a lot of times that is the query that matter, especially during the inference time. So what if we just allow these 2 heads to share the same key and values? And so what we do is that you can see here, I previously draw this data flow, I get this key over here, okay? But instead of doing that, what if I just let them use the same thing, reuse this key? Similarly, I can do this. I'm going to drag up, it reuse this value. I can do even more. I can actually even make this one to do this. Reuse the key. Okay, reuse the value. If I do that, what I can do is that I no longer need any of this. Then I can use this to close this. Okay, so this I no longer need it. Okay, and then this 3 thing we'll consider a group. So I will, what's the best way to draw this? So here, maybe here, I do this and highlight green. So this is my group 1. And they also have a group 2, and group 1 is here by itself. But we can potentially implement. Maybe this a good idea, right? So is this as easy as it is group query attention. So what do you save? You save you save a lot of parameters you don't have to train for. Also, since this KV are reused, you can put in the cache. It's called KV cache. It's referred to this. and you can load it once, but serve multiple query for the head. So and so empirically, that make a huge difference. So group query it coming around the time of Llama 2. So it started to use group query attention. Okay, so this turns out if you look in this way, not that hard to understand. Any more questions? How does early fusion affect multi-head attention in Llama 4? Let me think about it. I'll come back to that. I don't think I'm talking about multimodal today. All right, I think I have too much changes here. So I'm going to take a milestone by making a copy, create a copy here. So in case I messed up. Okay, what else can I do? I can do, should I do, maybe add more layers. What happens if you have more layers? So you go from, the layers doesn't change for 7 billion models, but you have a larger models, and turns out layers is what changed the weights the most. If we changed a few things, we have not significantly introduced a lot more weights, right? As you can probably notice. But if we add a new layer, what's going to happen is they just mark what the layers are. So layers come from here, from norm to self attention to multi-head attention, actually, and to all the way to here, right before the output layer. So there's one encoder or decoder block. So if I select this whole thing, can I select this? Too small. Okay, and I'm going to select all this row going up, up, up. Okay, it's kind of slow, but let's do it slowly so I don't break anything. So now a quick review of, you can now seeing group query attention, you're seeing self attention, multi attention right here. So this is my one block. Okay, and then copy, and I'm going to just reinsert right here, insert my copy cell. Now all of a sudden I have 2 blocks. So I just have to connect them a little bit. Let's just say, what do I do? Let's go maybe color them a little bit so I can distinguish them. So I'm going to color the first row, first column of the second block here is a different color. So just use this pink. Okay, so this is my second block. Let's just connect them a little bit. So yeah, this is actually automatically connected because of relative positioning. So this last output from the last encoded block get added to the norm. We can talk about norm and IMS norm later. So this is layer norm. It's being implemented over here, by the way. So, but this is gonna be the same. And this only thing different is that, so this will be taking first token from here instead of from all the way up in the top. So right now is all the way at the top over here. So I could move it down, but it's kind of hard to move this. I just major do it. It's not that hard. Move, 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 move. Ah, come on. I just lost it. Let's just re-implement this then. Okay, so I want to implement linear layer. I just do a metric multiplication and select all my weights and biases here, and then select my first token. So I have an extra one to take care of bias. So this is, I just re-implemented the linear layer, and the softmax is the same. So I did not change the softmax layer. So surprisingly, this the only thing I had to change, and I was able to add another layer. And everything's the same, but except that all these weights gonna be different, even though I copy and paste are same weights. But if you back propagate and stuff, they're gonna have different weights. Let's just look at that. What happened here? If you zoom out now, we have. Let me zoom out now. Now we have two encoder block. So you can visualize that the weights just increased by 2 times. And let me just make it prettier. I'm going to color this into a different color. So to show that we have 2 different blocks. Maybe this is faster here. So this is another block, the first block and second block now. Okay, so you can see how that grow. Okay, blue, is it blue? Okay, fine, blue is fine. So we have, now visualize it, we have 2 blocks, and we also have one group attention head, and each block has 4 attention, but it doesn't have to be. For instance, I could totally just remove this if I want to. What's most important, in my opinion, is the fact that they all have a fixed dimension of 5. That's how you can stack them up very easily. It's not a lot of dimension changes between the block, but they have dimension changes internally in the attention layer. For instance, you can see that from 5 to 334, and the other case from 5 to 333, and then concatenate, you get this bigger one, and you have to project back again. So this is necessary because you like them to have the same 5 dimension. Now we could pay attention to the linear layer. So this is a linear layer. Maybe we can talk about mixture expert right now. So this is one, you can see the one attention layer over here. Okay, do you need skip connection for the residual stream? Good question. So this is actually built in already. You can see skip connection, this purple, this orange thing. So that allows me to float all the way down, skip over here, and add it over here. So this is things that are being added. You can check the equation. So I'm adding the blue thing with this orange, red thing coming all the way from the above here. So if you, without skip connection, when we remove skip connection, it just basically just not doing anything. Just delete this. Now I don't have skip connection anymore. Okay, so if I do that, I'm gonna show you a feature of Excel. You probably, a lot of people don't know, but I found it very useful for teaching and for research. Is this thing called, where was I? I just remove the skip connection, right? So let's see if I do a trace precedent. You can see that I'm going to see that actually let's just zoom in a little bit. You can see the arrow. So if we do trace precedent, the Excel has a built-in building way to show this kind of pretty cool this back propagation sort of visualization. You can see how now this concatenation project back. It tell you they came from 4 different attention heads. And this attention head, if you trace back, and came from this dot product, and then came from this, eventually came from this input here. Do you see this? Kind of cool, huh? But if let's remove the arrow. Now, what if we add this skip connection back? Add and go all the way back up to select this. Select this one. Okay, now I've just restored my skip connection. And all of a sudden, you have this shortcut to allow your gradient to flow directly back here, right? And then to avoid gradient exploding, gradient diminishing gradient, the question, and also increase the performance. And you can also play the opposite. Where did this go? So you can do dependence. So you can go up, down. Actually, doesn't show me. How come? One more time. Dependent. Okay, see, go all the way down already. And dependent. And see this visualization. It's kind of cool. I like this. Can we have different model dimension after each transformer block instead of constant? Yes, in theory, you can. They cannot prevent you from doing it. But so let's see if I just purposely add this, to purposely have another dimension here. Okay. So this is my multi-layer perceptron V4 or positional wise V4 network. And so usually you take this input from previous layer, 5, and then you project up higher dimensional space to capture some higher order logic, but you have to project back to 5 so they be consistent. And just for the argument's sake, that's what I want to project back to 6 instead. So all I have to do is just have one extra layer of weight. Okay, 1. Okay, and then we'll fit. Now, just review 5 to 10 and 10 to 6. Okay, so this block has a different D model, so I have 6. But the thing is that then it doesn't fit here. How do you have to get 6 from 5? What can you do? What are your options to go from 6 to 5? The easiest option to, and then you introduce another linear projection in the middle, which will be a 5 by 6 matrix here. as you can visualize here. You can just, if you put these matches over here and do a linear projection, then you can allow them to match. Another problem with this mismatch dimension is that how do you even skip connection? If you want to bring input from the previous layer and it just doesn't match, you have to project them again. So that's what used to be the case for before transformer. When we were dealing with convolutional neural network, the original version or original ResNet, you have these dimensional changes over the stack. And another benefit of I just go back. I just Control Z my way back to where we were. Oops, too much. Just highlight this. I did this. Now I did this. Okay. All right. Oh, another thing is that you want to highly optimize, you figure out a way to fit this 5-dimension model most nicely on the GPU. You figure out optimization for that. You want to be able to use it for all your blocks here. And so you could optimize only once. They can be used for entire stack. Does it make sense? I hope. Oh, if a new model architecture is designed, how are the number of layers determined? Trial and error. I think it's just it's a trial and error as well. And then or how many GPUs do you have to train them? So only a few companies in this world have gigantic GPU farm. The my university doesn't. So if you look at 128, it's non-trivial. I mean, if it's, where was I looking at? Layers, where are layers? 32 layers. There's same, not that many, right? But huge. It's a lot of layers to train them. And there's 32 steps to propagate. Then you have a huge batch to have to go through for your gradient descent. It's very expensive. Okay, but now I want to talk about, maybe I talk about this one, V4 network. I haven't spent any time to talk about V4 network. Let's talk about the mixture expert. I think this is around this time when MOE is become popular. So there are some variant Llama 3 they started to use visual expert, but maybe not. But clearly Llama 4 uses MOE now. That's for sure. So let me just do a copy. I'll work on this copy. Okay, MOE, where MOE layer is happen to the MLP V4 network here. Okay, so so what does it mean by having 2 experts? Basically, this is my NLP block. I just copy this, and this is it. This is it. Now I have 2 experts. Not quite yet. I have to fix this a little bit. So this one is linear project from the input from the previous layer, output from the previous layer, and with this weight. So now I just have to modify this to select. Then I select the same. Actually, what happened here? Now I move this. Let's move. Doesn't let me. I cannot select this. Oh, here. Oh, here. Yeah, here. Okay, here. Okay. All right. Now I have done, and I have to take this together. So I will take this. This add this and this. I can just, the easiest implementation is I just going to place plus and just add this. All right. Okay. So now I have a most basic mixture of expert with with equal weight. Okay. I can repeat the same process, and to do my third expert, I'll repeat the same process, and I'll update my input to share the same input from before. And then I'll cut down here. I also just add the new output. Now they are equally weighted. So this is the equally weighted scenario. And then the question you have in your mind is that, but how can we have a mechanism that they are sort of linearly weighted, so they're weighted differently? Sometimes this expert get more weight, sometimes this expert more weight, sometimes this expert more weight. Also, we have 10 tokens. Maybe for a particular token, we like one expert to receive more weight than the other. So what we can do is that we could create another network over here. I'm gonna build another here called a routers network, and we need to have at least 3 different weights that we can calculate, one for each expert. So to map it out, what I want to do is that I want to have 3 expert. Each token will have neither weight. So I want to have a 3 by 3 by 1, 2 by 10. 3 by 10 of my gated value. This is my gate tensor. 3 by 10. Did I draw 10? Okay. How can I get 3 by 10 matrix from here? So we need a linear projection here. So let's just move everything to the right. Actually, I can do this. Shift everything to the right. I can have some more space to work with. So I'm gonna use this, insert, shift cell to the right. Will it work? Except I don't like this color. Let's just remove this. Okay, so I now kind of map this out. I want to have 1, 2, 3, 4, 5. This is my weight. This is how many weight I want. So I can do 0, 0, 0, 0, 0, 0, 0, 0. 0, 0, 0, 0, 0, 0, 0, 0. Okay, so this is how many way I just initialize to 0. And if I multiply, matrix multiply with my weights here, and then my tokens here, I just don't have binary 0, 0. Then I just put some random weights. So that's my random weight for computing gated value. So now I have all this. Okay, and then I would like to do a softmax. So these are my relative weights learned by this network. Let me just share this. So following the convention. So these are the learnable weights. And to implement softmax, so I'll do exponent of this by column and then sum of the same thing, exponent of this. So this is my softmax. You can notice that this thing is, even though it's at 414, but it's that if I show you more, let's zoom in more, you can see this 3 number will add up to 1. That's what softmax gives you. So I'll copy softmax over here. So it's all my softmax. So each one will be a get values across like this. So this is what the tensor looks like for your gate. And once we have that, I just lost track after okay. So I will bring this get value over here. Maybe just create some spaces here. I'll create some spaces here. And I'll put some get values close by here. So here is my gate value. The first expert will be this row. Okay. And then this per token that weighted slightly differently. My second expert will be, come back here, this row. And my third expert will use this row as the predicted gated value. It's all kind of high. And then let me just create some more space. I need some more space again. Okay, and then I will do an element-wise multiplication to take the output from the first one more time. Output from the first expert, multiply the gate value, this per token, and I'll have this gated, except that. Okay, and then this logic is the same for the other expert, so I can just copy the formula. So now instead of adding these 3 raw as a equally weighted combination, now I have a gated combination. So I go back to modify my equation here. So I just drag this down here. So now I finish my dense mixture of expert. Come on, here. Where's my hint? Doesn't, oh, here. Okay, here. One more. Doesn't let me, one more, move a little bit. Oh, here, okay. Drag here, down here. Okay, now I finish. And so for sparse, if that you pick top 2, for sparse, you have a mechanism that just pick 2 highest value and set the other one to be 0. For instance, 0, 4, 1, 0. So you can have a equation to do something like this. And then I use this as a gated value instead. There will be a sparse mixture of expert. But Excel, I find there's no easy way to do this, so I'm not gonna bother today. Okay, so so now I think I finished this as well. Mixture expert. Did I do mixture expert? Okay, so anyway, I think I could talk flash attention or just have a conversation right now. Is there a room for improvement within the domain of attention mechanism, NSA being the latest innovation of DeepSeek, or is there a natural boundary in your opinion? I think with NSA, it's native sparse attention. Like, do you want me to do that? For sparse MOE, do you normalize after selecting the top K? That, I guess, probably if you happen to have like a RMS norm along the way, so normalization is probably not as necessary because we'll like this to learn to normalize your value across your experts, and they are normalized in some way, but it can't. So it's no theoretical justification one way or the other, but I guess it's just empirically, if you commit to add a normalization layer and you committed 3 months to train your model, you already committed to it. It's too late for you to change to something else. But maybe the benefit is marginal, maybe there's no benefit, you don't know. But it also doesn't hurt for you to try. Okay, so so does input and output dimension for each expert match the model dimension? Yes. Also, it doesn't have to be. I could, for instance, what if I have one of the expert to output more? How can we have, say, expert 3 output more, a longer token? So we could add another row of weights here. So let me show you. Maybe add, I just moved by two spaces. Maybe add two set of weights. So it's similar to adding two nodes in this MLP right here. So now all of a sudden I have 7 instead of 4. So I update my ReLU here. ReLU is I think automatically updated here. Okay, here. So I've got 7. Now I have 7. The problem is that now you cannot add them together. Then what do we do? And then eventually, you most likely, then you have to project this down to 5 anyway, and to be able to add them together. Or you can concatenate, but concatenate, eventually you still have to project it to a state dimension to match with, to be able to work with other data. Just kind of Lego pieces, all these things, they have to have the same dimension for them to stack up together. You cannot have an arbitrary. So, but in theory, you can. Why not? You can just add a particular layer over here, and to add another linear projection to project back. So what I'll do is I will do 7, 1, 2, 3, 4, 5, 6, 7, and 5. So this is how much I need to then change. It's kind of ugly now. Let's follow the space over here. And then if I do a maximum modification, so we're back to 5 dimension per token. And then when I go over here, so I can move my green one over down here. All of a sudden, the equation works again. Okay, so now it's fixed here. So maybe I selected too many. Okay, here. Okay. What else? Should I talk about NSA? So the 10 minutes, do we want to hear flash attention or hear MSA? Or hear any of this? Rope, RMS, flash attention, NSA, native space attention. So sparse attention, so you can see that it is a dense attention. So we derive the entire query over here. Okay. So my understanding of the sparse attention is that, let me just use move a copy here, create a copy here. So this is my attempt to explain NSA. maybe. Based on my memory, I hope I'm doing it correctly. So what we can do is that now I have 10 tokens. What if I take 3 tokens here, okay? 3 tokens here and trying to merge into 1 token. So it becomes more sparse. Isn't it? Sounds like makes sense. Maybe this is the too big. Let's use a smaller one. Maybe here. I want to take these 3 tokens and then somehow condense all the information I need into 1. So let's just draw some space here. This is my goal. I want to take these 3 tokens. Let's just highlight a little bit. Green into this blue. Okay. So what do we need to do? So first we need to flatten this. So I have 9 elements here. And from 9 to 3, how do we go from 9 to 3? We need a linear projection here. So that way is 3 by 9 matrix right here. So I get lazy enough right now. I can use ring array and we get 3 row and 9 column. So I immediately get the matrix I want, and then I will just do a matrix modification. Matrix modification. Come on. Equals like matrix modification, and take this, okay, and then I take this. I cannot do this yet. I have to do is I want to do this, but I want to convert it into a column. 2 column. Too small, 2 column. I cannot see it. I said, but I just read it out loud. Okay, but then I get this. Now I'm done. Okay, so let's just see, just review this. Okay, so this is, and all right. So if I repeat the same thing for these 3, so I have this one, and I select the same weight, they share the same weights. Okay, and then the last one, another block here. So also repeat this, copy over here. I just select the same weight. Now I'm working with only 3 queries. Did you see this? Only with 3 query X. And then, so if I do the attention weight matrices here, let's re-implement this. So I'm going to create some space for me. Come on, this is ugly, but well, how do I fix it real quick? Just erase it. Sometimes it's trying to be smart, trying to figure out a format for me. Okay, and then so now I just redo this. I have my first query, and then my second query, and my third query, and then we do the same thing for my keys. I think if I copy and paste, might just work. Let me do it. Is it right? Oh yeah, actually, yeah, it works. And then you can notice that you have a different set of weights. Okay, and now I can do the same thing here. I want to transpose this. And then 1, 2, 3, and actually transpose another key, and transpose another key here. All right, and then all of a sudden, did you see the attention weight matrix? Oh, the dot product I need to do is only here. Comma, and select. Let me redo one more time. Make tree modification, select my key, and select my query here. And then this is, okay. And then usually I also have divide by the square root of the dimension of key, which is 3. So this is typical, but all right, so that's what we have. And then we take softmax here. I can copy the format here so it looks pretty. Okay, so now I can zoom out. You can comment on save the difference in terms of the computational complexity. So it's not sparse, I can see here. So instead of all this, now I have this. Okay, and then the native part is that this is part of the training. So I'm going to do this shading action just with emphasis, just to show you that. So this is what the native is referring to. You're training this as part of your sparse attention mechanism. Okay, let's just look at the non-sparse attention mechanism. How does it work? So if I'm going to take this into non-sparse attention, how can I convert this one into a non-sparse attention? Maybe just do a copy. Actually, maybe not. Let's just change it. So I have this matrix modification for whole thing. What I can do is that I could just do like this. And so in this case, each query is only going to compare with key in the neighborhood. So I can repeat this. I copy and paste over here and then select here and here. Okay, and then repeat this again, but I make sure I select the right key. Maybe in this time I just do 4 of this since it's a multiple of 3, but the last one multiple is 4. Okay, so now it's a lot sparse. Do you see this sparse? And this is dense, and this is dense. This is sparse. But the difference between this, I just say, okay, matrix neighbors. There's no extra learnable parameters involved. There's no extra network you learn to do this. But in this case, if a native sparse attention, it somehow works. You have this. And I thought, this is, you can visually see there's an efficiency in terms of the computational efficiency, just fewer matches compute, but you have to give DeepSeek credit because theoretically it sounds fine, but you talk about tens of millions of dollars to even just experiment to try to see whether it works. What if it didn't work? It could be the case that they tried it didn't work, but they tried it anyway, and they are lucky they worked, and so they probably take the report about it. But I bet they probably try 5, 6 other things that didn't work, so they never talked about it. Oh, so this is like a convolution with try-3 with no overlay. That's correct. What else? I think we're running out of time. 2 minutes. I enjoyed it. Although I have, I can show you my practice sheet. So real quick. So if I stop share and share again this is my internal practice. Not as pretty, but if you're wondering, so this is, I have, so this is, the things I did not talk about today is the, so this is from layer norm to RMS norm. And then what else did I talk? And also I talk about, oh, here. So this is rope. It's kind of complicated. Yeah, this is rope. Rotational position encoding. But I think I can tell you the high level stuff. So you can see that I put this block of extra computation. Number one, it's not shaded. So this is not trainable. It's all pre-computed. All the rotation matrix can be pre-computed. Number two, it's really close to the attention head right here. Whereas the original positional encoding is only injected right in the beginning. All right. And then you hope all this git connection to bring information down. Now you have 32 layers to do so. And you're lucky if the position encoding has any impact down the stack. But with rope, you would add this computation at each head level, every single stack, get the position really close to where the attention matters. So that is probably the takeaway, that being able to visualize the difference between the two. This is a way to visualize this. Like this rope is right here, but traditional positional encoding is at the top. There's a difference. Okay, so hopefully I still talked about everything, not at the same level of depth, a bit unstructured, and hopefully you guys have fun. I have fun.
Very, very fun. It's always good to see a different perspective on how this stuff works. I'm sure people got a lot of value out of that.
Yeah, this reminds me a lot of like Ishan's walkthrough, but like actually higher level, like you did a lot of work in like reducing the dimension so that we can actually hold it in our heads, which I think is very important.
Yeah, This is an inductive process, and then if you get 3-dimension right, then you in the future I see just vibe code.
Say 14.
You ask the model to expand this to a higher dimensional space, but underlying math is easier to work out at a lower dimensional space.
Cool. Well, just to be respectful of your time, if people want more, where to best find the rest of your work?
So I really enjoyed it. So honestly, I
Yeah.
don't tend to get to talk to a technical audience like that. So I went all out today. So I was curious how it's being received because with my own student, I cannot go at this depth. I mean,
Oh,
cannot
that's
go
okay.
at this pace. So I get to talk in one semester worth of stuff in 1 hour, and I expect that you could follow most of it, or all of it. So I enjoyed it to give me the opportunity to go nerd
Yeah.
on this.
Okay. Awesome. Yeah, I mean, we've been covering a paper here every week for the last 2 years, so there's been a lot of interesting lectures and papers, and yeah, definitely like some of this is repeated, some of this is new, or like
Yeah.
a new perspective on the same thing is actually always useful.
So did the Excel online live up to the fast enough for you to check to walk around the worksheet? I'm curious from your side of experience. What is this like?
Steve Saito says Excel is plenty fast.
And you were able to also check the equation formulas and yeah. Anyway, okay. I did prepare. I thought it was fun, so I spent quite a lot of time to think about how I should cover this. And I'm glad that most of you still stay. And we'll hope to do this again for some other things I didn't get to cover.
The live spreadsheet was very, very useful. I feel like I still have a lot to dig back into, but yeah, the formula is showing what's
Yeah.
multi-headed detention, transposing and stuff. The little back prop was crazy. Very, very cool.
Okay, thank you. Thank you for the invitation for facilitating this opportunity. I hope that I'll have opportunity to come back and because then I can geek out with you.
Always. I think for next week, I'm probably gonna invite someone from Prime Intellect to cover Intellect 2. They put out a paper on that this week. So what do we think?
Distributed GPUs on the blockchain. Let's go.
Blockchain. Sounds good. And
Seems like a good paper. So we'll invite their team over. I'll share the paper and
Yeah,
stuff on Discord.
I think like the interesting thing is like, does RL and long chain of thought sort of training actually introduce new training paradigms where the hardware requirements are actually different and they actually don't benefit from the normal centralization factors.
Yep.
Cool. All right. Well, thank you so much.
Cool. Thanks, everyone.
Bye-bye.
so Sean,
Yeah.
is it possible that you can share with me the chat history? How do I save it? Because there's a lot of good questions I'd like to get.